Thank you, Dan. I represent the work of my group that's called the Radical Group, and a lot of the papers and software can be found at the following website. So my talk's really 3 or 4 main points. I'm going to spend some time trying to argue for a fresh perspective on workflows, some history, some context, and represent and establish the tools that our group's developing as a fresh perspective, as an implementation of many of the ideas that a careful analysis of workflows and workflow systems produces. I'm actually not going to talk about many computer science results because last year in the Blue Waters Symposium, I introduced Radical Pilot and showed how careful design and implementation allows the efficient launch and management of about 100,000 tasks over 64,000 cores. And remember, each task is an independent MPI job. And in order to reach these kinds of scales, the ability to launch about 100 plus tasks every second required us to do some invasive systems programming with OpenMPI through the ORT and DVM. That's published. Again, that's why I'm not going to talk about this. But where I do want to spend some time is to show how we've put all of these systems, software advances, and workflow concepts to use, and namely to try to get better science results in collaboration with colleagues at Rice University and the University of Nottingham. And in a nutshell, it's how, with all of these complex workflows, you can get better sampling, and the details will become clear later. But for the computer science part of it, although I'm not going to talk about these details, what I do want to leave you with is a single message. If there's one message you do take out from this talk, it's the following: that in the presence of careful design principles, abstractions, and execution models, the distinction between high-throughput computing and high-performance computing is rendered meaningless, if not completely incorrect, or maybe, as Pauly would say, not even wrong. And these are often historical artifacts of software and the lack of design principles in our software. Hopefully it'll become clear over the course of the rest of the talk. So, Radical's laws of cyber infrastructure. Won't talk about the first law of cyber infrastructure, but really get to the second law of cyber infrastructure. Namely, every application execution tool eventually claims and grows to become a workflow system, right? There are interesting corollaries. There's the less pleasant corollary, which I don't put here for the record since this is being recorded, but other talks will, if you do a bit of digging, will tell us that we don't know much about workflow systems. But the more sensible and academically relevant one is, to prevent the proliferation of workflow systems, we need to determine the right components, basic building blocks, to enable most workflow systems to grow and not to repeat and start from scratch. Okay, and Radical Cyber Tools are a research endeavor to try to test these ideas, to put these ideas into both conceptual tests but also practical tests. And there's a lot, and this is an hour-long lecture into itself. The way we conceptualize the overall cyber infrastructure stack, and as they say, all models are wrong, some are useful. This is a model of trying to think of the overall cyber infrastructure stack. 4 levels. Right at the top are the applications, the application workflows. At the lowest are the infrastructure. The 2 of relevance for this talk are what I call level 3 and level 2. Level 2, the task runtime system. Remember, a task could be an MPI job or a standalone single core job. And if you will, workload management systems, not workflow. And a workload, as distinguished from a workflow, is where the a set of tasks where the dependencies have been resolved and there's a certain amount of concurrency, and what is left is the decision about where and when to run them, not necessarily resolving the dependencies. So in some ways, a finer grain than the workflows themselves. And so the ones in reds are the components that are of relevance to trying to establish workflows on Blue Waters. And I'll briefly talk about Radical Pilot and the Ensemble toolkit. Right. So, as mentioned, radical cyber tools are a laboratory for supporting production-grade workflows and workflow tools while supporting many of these research ideas, and clearly a very complex set of components. But the message here is twofold. One is existing workflows systems can utilize radical cyber tools. And here are 4 examples of existing, very well-known workflow systems that have used radical cyber tools. The first, Swift, which again many of you know and have used, has used radical cyber tools to try to support a execution model, which I'll talk about later, known as the Ames execution model, and this was work done in conjunction with Dan Katz. The second very well-known workflow system, Fireworks, which supports about 50% of the entire materials genome calculations on DOE and elsewhere, they are using, or I should say investigating, the use of radical cyber tools in very much the same way as Swift has. How can the integration of radical cyber tools, in particular Radical Pilot, support scalable heterogeneous workloads without the Fireworks framework having to do a lot of the systems engineering? The third is Panda, or Big Panda, which many of you will know is the main workhorse of the Atlas LHC experiment. And just to set the scale, Panda at any given instant of time is supporting about 300,000 cores distributed all over the world. So if you do the numbers, this is order billions of hours, core hours a year. And at any instant of any day, beg your pardon, about 1 million jobs a day, right? And Panda is using radical cyber tools at multiple levels. There's the Saga level, but also the pilot level, to try to bring what has historically been called high-throughput computing onto high-performance computing. Many different stories here, but the one story I want to tell you is that of the usage on Titan, where now approximately 100 million core node hours, beg your pardon, a year are being used by Panda. Now, for those of you in the know, Titan is a machine very similar to Blue Waters. I think Blue Waters might have a fewer larger number of nodes, but there's a certain, the total, there's distinctions which I won't get into. And this is just trying to show you how by the use of Pandas being integrated with Titan, there are on average about 10 million node hours being used. And that's about not only a very significant fraction of Titan, but that's about 5% of all of Atlas's workload coming onto Titan. Now, historically, this is what the grid was invented or set up for. But you start seeing the kind of blurring of lines between the distributed high-throughput systems and a very large machine such as Titan and or Blue Waters. And the last example is the binding affinity calculator coming out of Peter Coveney's group in London, which is used for many biomolecular studies, but in particular, the ability to study the binding free energy calculations. And the whole setup is using radical cyber tools, and that particular product is called the high-throughput binding affinity calculator, being used for several cancer studies right now, so on and so forth. So just 4 very quick examples of external tools which have nothing to do with radical cyber tools at the point of conception and development, but have over the years started integrating aspects of radical cyber tools. I then move on to talk about tools that have been developed on top of radical cyber tools to support workflows. And in the interest of time, I'll just talk about Ecstasy. This is advanced sampling tools. And what Ecstasy uses is an underlying component called the Ensemble Toolkit, which, as the name suggests, is really to support the concurrent execution of a very large number of ensembles. Now, sometimes these ensembles are completely uncoupled. Sometimes these ensembles have varying levels of coupling. Think replica exchange, think some global coordination or synchronization after a large number of steps. And the important point here is that the same conceptual models, the same execution models that were used to unify the distributed high-throughput computing, worldwide grid computing onto machines such as Titan, are also used to support the concurrent execution of a large number of MPI programs. That's, I think, the first lesson I want to reiterate. The conceptual unification of high-throughput computing tasks with what is purely a large number of MPI tasks. And that's the Ames model of execution, which then has been extended to what we call the radical execution model of a large number of concurrent MPI tasks. So, as I said, we won't talk about the performance numbers of Radical Pilot on Blue Waters, but for those of you who may not be familiar with the pilot concept, let me just briefly define what the pilot concept is. And we heard bits of that in Paul's talk this morning. It's really a scheduling overlay which generalizes the recurring concept of utilizing a placeholder job in which you then place a larger number of smaller jobs. The so-called theory of pilot jobs has been developed by my group over the past several years, called the P-star model. And fundamentally what this does, it decouples the workload management from the resource management. So whatever your resource might be, you acquire the resource without worrying about which tasks go where. Once you've acquired the resources, you then manage the slicing and dicing of the resources, so you have much greater control, both spatial and temporal. What is important about the approach we've advocated is not only is it a conceptually well-defined approach of managing these resources, but because of the presence of well-defined APIs, you can build higher-level tools and workflow libraries. And that's what the Ecstasy library is all about. Just to remind you that on Blue Waters, we had to go through several months, if not years, of careful engineering with the open runtime environment of the OpenMPI implementation. And this was in order to get to the approximately 100,000 tasks to be launched in approximately 10 seconds. And there's lots of details, but as mentioned, a lot of these details were presented last year. We're now extending this capability, hopefully to MPitch as well. Okay, so now in the last 5 to 7 minutes, just want to say, put all of these things together and say, this is not just computer science and systems engineering, but by being able to do all of this, you can do darn better science. And the better science that I'm alluding to is better sampling. So if you had an extra $1 billion in your back pocket, you'd take this approach to trying to study the problem of BPTI. BPTI is a protein. This is from D. Shaw. And if you run this for about 800 milliseconds, you start getting what is this interesting phenomena. But not too many of us have a few extra $1 billion in our back pocket, so we have to kind of introduce innovation in sort of brute force, and this is where a lot of the sampling advances in sampling have taken place. So can you start seeing phenomena like this without the freedom and the ability to run such long simulations? And this is where a large number of members of the community are thinking of better sampling. And one particular approach called the COCO, Collective Coordinate-Based Approach, which is PCA-based unsupervised learning. I won't get into the detail. But I will sketch out the basic ideas. You start with a set of ensemble members and you let them run for a short duration. After a certain number of time steps, let's say corresponding to 1 nanosecond or a few nanoseconds, you checkpoint, you do some collective analysis, in this case the PCA-based, the COCO, PCA-based unsupervised learning, and then you restart these simulations and you repeat, rinse and repeat as this shows. You rinse and repeat this many, many times, and you start sampling phase space. And the question that I present to you is, if I gave you, let's say, 1 million node hours of computation, would you do better in this approach where you do a large number of ensembles, checkpoint, do some analysis, and then start another round of a large number of ensembles? Or would you be better just running them, if you will, either as one long simulation or many uninterrupted ensemble simulations? And the answer to that is you're much better off using this ecstasy-based approach of large number of ensembles, checkpoint, do some analysis, and then use those to run the next round of simulations. And lots of details here, but I'll just try to catch your attention by trying to show you in this magenta is the ecstasy-based approach. And this is the cyan color represents when you run just the ensembles. And two important points here. The first is if you think of greater volumes sampled in phase space is better, then you can see that that approach just naively samples much more of the phase space than direct ensemble-based simulations. But another more careful, detailed way of looking at it is that if you look at clusters, remember, not all parts of phase space are equally interesting. So think of 7, in this particular case, 7 clusters that emerge, clusters as in regions of phase space. You can see that the magenta samples all 7, whereas the traditional ensemble-based approaches barely gets to the 5th. So again, lots of details, but the primary message here is that with this simulation analysis iterative loops, you get much better sampling than if you just did your direct ensemble-based. And this is, again, another way of looking at the same data, what is known as the median first passage time. You can see that the median first passage time in the ecstasy-based approach significantly smaller than in the traditional ensemble-based approach. And this is, again, lots of details here, just to tell you that the results in the previous slide, this slide, are not just a random coincidence. It wasn't a cynically chosen point in phase space. It was carefully determined, and those results hold in general over different parameters of the workflow. So just getting back to telling you how we achieved this, this is where I show you the beauty of the tools that we've developed. Weak scaling plots of up to 2,048 ensemble members concurrently running, consuming about 64K cores, and this is all on Blue Waters. And just to try to show you, this is, again, not just confined to one particular point in phase space, but for a different physical system and for different counts, both the strong and the weak scaling. I think my time's up, so I shall try to wrap up in the next minute or two. I hope I've convinced you that you need a fresh perspective to workflow system. You need and Radical Cyber Tools presents one particular approach and a whole way of thinking about different workflow systems, the building of different workflow systems. Hopefully I've shown you the fact that if you have abstractions and execution models, then the distinction between high throughput computing, distributed high throughput computing, high throughput of high performance computing and high performance computing are rendered meaningless, and they can be brought around under the same conceptual framework, but also, and importantly, under the same implementation. And this takes us away from meaningless discussions around software and workflow systems and gives us a more principled design and development of general purpose middleware. And I've shown you that thanks to the workflow tools developed on Blue Waters, we've demonstrated far better sampling, orders of magnitude better sampling when you use these sophisticated workflow systems as opposed to direct, naive ensemble-based simulations. Thank you for your attention.